Hello, everyone. We'll get started. So this section has two parts to it. I'll be taking the first part. We're going to be discussing the convex hull. This whole session is on thermodynamics. So I'm going to talk about the convex hull, and then for about an hour, and then we're going to have Rico Frederick come up and he's gonna discuss some important corrections for polar materials. Okay, he's got a method for correcting them. All right, let me share my screen. 1 second. And if you want to follow along with the slides, they are. Oops, 1 second. Okay, they're going to be in the. If you open up AFLOW Day 2, you'll see that these are the slides for the first part of the session. Okay. All right, let me just make sure I have the chat open so that I can see if there's any questions. 1 second. Okay. And all right. All right, perfect. Okay, so we're going to be discussing thermodynamics, and we're going to focus on the convex hull application. It's called AFLOW-CHULL. Okay, so an important question, and it's a question that I think you should always be asking about the materials you're studying, is whether or not the material is going to form. Okay, so the remainder of this section is going to be addressing that particular question, is whether material is going to form. So there's two types of controls that dictate whether material is going to form. There's the thermodynamic control and the kinetic control. This picture might look familiar from chemistry of how you look at product reactions. So you have your reactants and you have your product, and the path there, you have to look at the energy landscape of how you get there, right? So it looks like if you just look at the lowest energy pathway, this is going to be P2, this product 2. But if you look at the pathway to get there, it's actually much larger than P1. Okay, so this is demonstrating the difference. So thermodynamically, P2 is more stable, but kinetically, it looks like it's easier to achieve P1 because the pathway there is shorter. So I just want to demonstrate the difference between thermodynamics and kinetics, and both are very important. Okay, and so the remainder of the talk, we're going to be discussing thermodynamics. Okay, so how are we going to determine whether something is thermodynamically stable? This is ultimately the tendency of materials. Okay, so given the amount of time, infinite amount of time, you're going to explore all the possible states that are available, and so you're going to end up really seeing P2. But okay, so thermodynamic stability is a question of whether, if we have a material, here I have an example, palladium, platinum material, we want to ask the question, is it going to decompose into its components of pure palladium and pure platinum? Okay, and that's going to be dictated by the energy of the reaction. In this case, we're working with the Gibbs free energy. Okay, and so this is just the thermodynamic potential. There's others that are of interest for different reasons, but in experiment, we really want to know about it's easier to control temperature and pressure. So that's the potential we're going to work with. So we have two terms. It's the enthalpy term, and then the disorder term. Okay, so you can think of this as order versus disorder. Okay. So this is entropy, and it's scaled by temperature. Okay, so what does it mean to be at equilibrium? Well, it's a two-part answer. So it means that we've minimized the Gibbs free energy while also maximizing the entropy. Okay, so both have to be true for you to be in equilibrium. And for this talk, we're going to ignore the entropy. The entropy is going to be important for tomorrow morning's talk on disorder. But for right now, we're just going to focus on the minimizing the energy. Okay, so here we have a plot of I'll spell out what the formation enthalpy is, but just think of it as energy. Okay, So we have the energy on the one axis, and then we have the concentration, the full concentration range on the bottom between palladium, pure palladium, and pure platinum. Okay. And so what are these markers that we have here? Well, we have a marker here at pure palladium. We have a marker at pure platinum, and then we have a marker at the 50-50 range. Okay. So each one of these represents a structure, right? So think of an actual arrangement of atoms, a prototype, just like we discussed with David's talk. And so from this plot of energy versus concentration, the question of whether it's more stable to exist as a combination of palladium platinum or to separate into its pure components is really just a measure of how much lower, which one's lower. Okay, so that's what I want you to think about. Which point is lower? So the fact that the palladium platinum is lower in energy than the two components here, and really I want you to focus on the line. There's a tie line between them. Okay, so it's lower than the tie line between the two components. That means that this structure is preferred over decomposing into its mixture components. Okay, and this is the Gibbs free energy. Since we're ignoring the entropy and the temperature, right? We're working at zero temperature. These are density functional theory calculations. We're working with the enthalpy, which is just that ordered term. And really we're working with what's called the formation enthalpy, which we talked about in the last session on database, because it's a property we calculate. So what is formation enthalpy versus just the enthalpy? Well, the formation enthalpy, if you notice on this plot, I didn't even mention it, but on the plot, the pure components have zero energy. That's not true. It's a material that's going to have some energy. So we've zeroed out the energies of the pure components. Okay. So really, this could be at minus something over here. This is going to be minus something here. But by zeroing out the energy of the endpoints, it's now visually easy to see that this is much lower because it's got negative energy with respect to its components. So that's just the formation enthalpy. It's just the difference of the energy of this system, the raw enthalpy, minus the enthalpies of the pure components, so that you get a plot like this, okay? So it's zeroed out. So we don't just have 3 types of materials in the database. We're going to have many. So for this palladium platinum system, AFLOW has at least 527 entries. This was calculated, a few months ago. It's probably been updated since then. We might have a few more. But we've done a good job of, and now you kind of understand why we have the database organized the way it is, because we're going to be exploring, ranges between palladium and platinum. So we look at that section of the database. Okay, so these are all the prototypes in that directory, if you remember, in that tree structure of the database. So we have the pure component here, but we're going to have a bunch of other structures, right, of different arrangements and also different concentrations, where they are in the x-axis. And all the different prototypes are going to have different energies. Okay. So now we're not just talking about being lower than 2 points. We're talking about being lower than a whole combination of points. Okay. So stability is really a combination of which it's which one am I going to be lower than all of the other tie lines on the plot. Okay. So you have to really look at all of the tie lines, not just the tie lines at the top, right? Not just these 2 tie lines. And so you have to look at all the tie lines, and the most stable points, the points that are thermodynamically stable, are the ones at the bottom here that I've highlighted. Okay, so this is called the convex hull. It's actually a mathematical term. It refers to, you can imagine that we took a giant rubber band around the whole data set. Okay, and then the points where the rubber band touches are the most stable points. They're the most outside points of the data set. Okay, so these are the points that are going to be the most stable, and so I want you to remember that rubber band, because that's going to be the best visualization of what we're after here. Okay, and so this is what's nice. Gibbs was a very visual person. I've talked to some people and some professors who looked at his work, and he's had all these drawings of how he understood things. So this is what's nice about it. It's a very visual understanding of thermodynamics. So we have a point here that is not on what I'm going to call the convex hull. It's not one of the stable points. Okay, so we have a point off the hull, and it's above the hull because it's going to be above the hull because it's not the lowest point. So this point here is not stable, okay? And so what does that mean? It means it's going to decompose. It's going to decompose into its components. The most stable components are defined. This is exactly what I want you to do. I want you to take the point and just drop your eyes to the part of the convex hull directly below it. And the 2 points that define the facet, this is the terminology, facets. This is a facet of the convex hull. The 2 points that define the facet of the convex hull, those are the stable points that it's going to decompose into, okay? So you can see here, it's this component and this component, and of course you have to balance the equation. So if you balance the equation, you get 0.6 of the half and 0.4 of the other, and that balances the stoichiometry. Okay, another interesting thing about the visualization here, this distance in energy, that's going to be the energy driving that reaction, okay? So in this case, it's kind of small. It's 3 MeV per atom. So what it means is that if the energy is really high, that means that it's really going to want to drive to decomposing, okay? So if this distance is really large, it's really unstable, it's going to really have a big tendency to decompose. If it's not so high, if it's very close, in this case, it's actually kind of close, and we're close, I'm going to define close in a second. It's not that close. Because we're at zero temperature, remember, it's an approximation, it might actually be a stable point in the sense that it might be a material that is actually experimentally verified. Okay, it might be something that actually forms at room temperature, let's say. Okay, so the error here, if you will, if you want to add an error here, it's about the kinetic energy, the kinetic excitations at room temperature, which is this magic number of physics, 25 MeV. Okay, so if you're doing an analysis of whether a material is going to form, whether it exists, let's say, being within 25 MeV of the convex hull, you might say there's a good chance that it might exist. Okay. All right. So the algorithm here, just some details about the background algorithm, what's doing, and what's the power of having all of this in one framework, right? This is all AFLOW. It's not just prototypes. It's not just database. All of it's tied together to use these tools. So we might have a hole in the database that looks like this, okay? And so we have an outlier system here, all right? So this outlier system, it might be legitimate that this single material is that much more stable than the others, but probably not, okay? And so when we're doing these high throughput statistics, we see this and we say, okay, this looks like an outlier. It could be a bad calculation. It might have been run with different input parameters, and we didn't check. We didn't know that it was on different input parameters. For the most part, we've done this analysis for everything. The database is very clean, but I'm giving you an example of why this material might be, why something like this might exist. Well, if it does exist, we do an analysis and we remove it. Okay, so we do an outlier detection and removal automatically, and it's something you can turn off. We can talk about that if that's something you're interested in. Another thing that's of interest is that we have a lot of points in the database that might be considered duplicates. Okay, so we pull data from different repositories. We might have duplicate structures, and just like the session from this morning, we can very easily determine, is a structure a duplicate? And so it might be that we've pulled from different repositories, so we have duplicate data, but it might also be something that it started off as a unique material, but by the process of a DFT relaxation, it converged to another material. Okay, that happens too. So the point is that we need to analyze what are the unique materials. Okay, and that's how we want to make the convex. We want to make it with a unique set of structures. So we perform structure match, X-crystal finder, right? The crystal finder. So this algorithm it's available in the code base, and so we leverage it for building the convex hull. Okay, so we're going to go online now, and we're going to play with some of these convex hulls. So if everyone can navigate to, everyone can navigate to AFLOW.org/AFLOW-CHULL. Okay, 1 second. Okay, so if you want to navigate it by the web address, you can also come at it from the main page, and I'll show you how to do that really quickly. You want to go to the Convex Hull app here. Okay, so as an example, we're going to look at the silver, gold, and cadmium system. So go ahead and type that in, and we're going to hit enter. Okay. So here we have a visualization of the silver, gold, cadmium convex hull. Okay, so you can spin it around, you can zoom in and out, and you can actually play with this. And so what's nice is you can actually visualize and see what's going on with the points here. Okay, so there's a nice zoom feature here, and you can click on points. Okay, so you can see I've accidentally clicked on some of these points here. So I'm going to show you that if I click on a point here, it'll take a second because it's grabbing the data. It's actually using AFLOW to grab the data. It'll pop out with a card, and it'll give you some information about it. So this is a non-ground state. It's not one of the points that define the convex hull. You have some properties about the material. Okay, it's just some ones that might be relevant. I'll talk a little bit about what these are in a second, but this is the distance to the hull. I've already mentioned that. These are just some properties from the database. If you go to more info, it'll actually pull up the entry page for that material. Okay, and so I think we've already talked about this page. You have the JMO here, and you have all of the properties that you need. Okay. So all the data is really well integrated. Okay, so if we go here, I'm going to go back to selected hull. That's that second point here, and you can do a few other things. You can toggle points on and off. You could so if you just want to look at the landscape, you can do that. You can toggle labels. You can just highlight the hull points. Okay, so they pop up here. You can pull that information. You can reset. It took you back to the main page. I'd have to take a look specifically at what you're doing, but we can look into that. But yeah, it's possible. Actually, could you send the link? Because it's possible that we might have to update something. So if you send the link, we can actually we can debug that if it did indeed send you back to the main page. So okay, so the other thing that it can do is you can download a PDF. So go ahead and click download PDF. Perfect. Thank you very much, Sarah. We'll take a look. Okay, so now we have a nice visualization here. So this is a PDF. You can actually download this and carry it. And I want you to treat it like a working document. So here we have the convex hull illustration with the hull points highlighted. And you see that so these are all the stable points on the material. It doesn't include the stable points in the picture, the non-stable points rather. And you see that we have a coloration scheme here for how deep the hull is for that part. So you see it's deeper here than it is in the other parts, okay? So what's nice is that, so we have the picture here. We write it in kilojoules per mole, and as well as formation enthalpy, MeV per atom. We have the table here that's organized. It's a few pages long because there's a lot of entries it pulled for. And so we start with, so if you highlighted a ternary, you're probably interested in the points that are actually ternaries, not the binaries and the unaries. But of course, those are important for building the convex hull. So we start with the ternaries, and you see here that we have. I'm gonna zoom in on this. So we have a lot of data that we're putting here that might be relevant to you. So the first one here, it says it's unstable. I organized them by concentration. So this is an unstable system. For all the systems, we list the prototype, the AUID, the relaxed and the original space groups. Okay, so you can see if there's a difference. We list the spin per atom of the system, the enthalpy of formation, the entropic temperature. Don't worry about this too much. This is a parameter that we've defined that it's basically the ratio between the ideal, it's a ratio of the ideal entropy in the system. So this is based on concentration divided by the formation enthalpy, okay? But I wouldn't worry too much about that. We're not gonna focus on that, especially not in this talk. And then this is the distance to the hull, okay? This last column here. So since it decomposes, you're gonna have a decomposition reaction written here, and you have the full balanced equation. So you might notice that there's some links in the PDF. I'll show you where these links point in a second. Now this is a ground state system. And since it's ground state, I highlight in green the system that is on the hull, okay? And I want to see if I have another example. Yes, I have another example here that I'll show you. So we have two systems that are highlighted because these two systems are equivalent. Through the crystal finder, we can identify that these are actually duplicates. So we highlight them both. The orange that you see, the orange means that it's structurally similar. Okay, so how do we determine structurally similar? Well, we look at the relaxed space group and we say, is it at least of the same space group as the one that's on the hull? So those are the ones that are highlighted in orange, and take it for what it is. So it's a stable point. So what I'm identifying here are the vertices or the facets. So for this system, I'll show you what I mean on the picture. So on this picture, we have a bunch of facets, right? So we have this facet that's defined by these 3 points. We have this facet that's defined by these 3 points and these 3 points. And so all of these neighboring facets that connect on this point, that's what we list here. Okay. So they're in 3-phase equilibria with the point of interest here. Okay. The last set of data that we have listed here, this is called the stability criterion. I'll show you what that is in the slides, but it's a measure of how robust the system is. And then this is called the N+1 energy enthalpy gain. I'm not going to talk about it in this talk, but I will. This is a very important parameter for a disorder, and I will talk about why that's important in tomorrow morning's talk. But this is used for disorder, okay? And actually, I'll show you a visual what's going on. So we have, I believe Stuart was he's among the participants today. It's one of our students, and he's been doing an excellent job. We have a new version of the Convex hull that's coming out, and so this is not available yet, but it will be very soon. But I just want to show you some of the work that he's been doing, because he's been doing a great job of visualizing. So if you click on points, so I'm going to click on this point, it actually shows you the decomposition. Okay, so look at how nice that visualization is. So you can actually see exactly what it decomposes into. And so you see this point actually sits right on top of a tie line. So it doesn't decompose into 3 points, it actually decomposes into 2. In the visualization, the algorithm considers that. You know, you might imagine that if a point sits directly right above the triangle, it's going to decompose into these 3. So let me see if I can find such a point. It might be a little hard to see. Oop, 1 second. I select this point here by accident. Okay, this is also a tie line one. You see that we're doing a good job of picking our tie lines. What about this one? Okay, so this does decompose into 3 points. You can see it. Let me try to zoom in. Yeah. So you can see that it does decompose into 3 points, and you see what facet it actually falls to. This analysis is incredibly visual, so that's why it's nice. Okay. So just to give you a taste of what's coming tomorrow, I know I said I'd talk about it tomorrow, but what is the N+1 energy? Well, it's going to be the energy of, okay, so we define the convex hull here. Again, I'll talk about this more tomorrow, but I just want to show you because we have the visualization up. This convex hull is built off of not just the ternary points, but also the binaries and the unary points, okay? So this convex hull is defined by all 3. What if we remove the ternaries and define the convex hull, okay? So in this case, the hull doesn't change very much. But I'll pull up another hull here where you see that one of the points here that is on the hull that actually really brings the hull down as a ternary point. So if I take that off, the blue here represents the convex hull without that point, okay? And this is a related concept to the stability criterion, which I'll talk about back in the slides. But really what we're doing here is we're visualizing the convex hull here without certain points, okay? So that's the visual here. So if I turn it back on, this is the real convex hull. If I turn it off, that's the pseudo hull without it, okay? So keep that visualization in mind for the next set of slides. Yeah, so it's not available yet. It'll be coming out very soon, but I wanted to show off because Stuart's been doing such a great job. Let's see, where are my slides? Okay. So we've gone through this. Okay, I want to talk about the stability criterion. Okay, so stability criterion, just as we visualize, this is what it looks like in 2 dimensions. It is so the stability criterion is defined for stable points. And what we're going to do is we're going to remove that point, recalculate the new hull, and find the distance of this point up to the fake hull. Okay. So what is this measuring? Well, remember that this analysis, it depends on your sampling. Okay. So we've sampled 500 points here. So it's a very nice sampling, but clearly we haven't explored every possible structure that exists because it would be impossible. There's so many structures we haven't even thought of yet. So this is a metric of how reliably stable this structure is, given that there could be points that offset it. Okay, so if this distance is very large, then it's not going to be too likely, given that we've converged the hull, it's not going to be too likely that we're going to find another point that's going to remove it from the hull because it's more stable. Okay, so it's a heuristic, but we've actually been able to leverage this heuristic. We have some collaborators in Ireland that we did a work with. We have some of their students here today with us, and we did an analysis on the convex the convex hulls in the AFLOW database. We looked at the Heusler structure. Okay, so there's 3 variants of the Heusler structure: regular, the inverse, and the half Heusler structure. And we looked at decorating these compositions. Now you understand what decorating is, with all of these different metals here, all these different elements here, okay, which are mostly metals. The Heusler systems are interesting because you can actually have systems that the individual components are non-magnetic, but the overall structure, when you put them all together, turns out to be magnetic. So we're interested in finding new magnets, and it created over 200 different candidates. And among the things we searched for was this stability criterion. So we said we're only interested in systems that have a stability criterion of at least 30 MeV, which is higher than that 25 MeV of room temperature. Okay, those room temperature excitations. And that stability criterion was used as a heuristic to filter out the other systems. And of those systems that we reduced the set down to very few. And of those, we discovered 2 new magnetic systems. Okay, this was with Professor Sanvito in Ireland, and we discovered this is one of the systems here. This is cobalt, manganese, titanium, and here we have a visualization of some of the experimental properties, the magnetic moment. So it is indeed magnetic, and we studied the structure here, and you can see the structure the structure matches that of a Heusler system as we predicted, and it's single phase. Okay. So this was a successful application of these sort of parameters to actually discover real materials. Okay, so I already walked through this. Okay, so now we're gonna go to the command line, and if you like, you can run them with me now. But I'm gonna kind of breeze through, and then we're gonna work together in our breakout rooms, and you can actually run these commands. Okay, so let me pull that up. Okay. Well, no, I want my slides up too. Okay, so you can actually run okay, so I'm just going to show you what the commands are here. So you can run from the terminal using the AFLOW binary. You can actually calculate the hull, and you can get it back in a number of different formats. So you can get the PDF that we explored, we played with online. You can actually print out that PDF. You can also get a text document. Okay, so this is nice for actually, it's kind of a table written in plain text form. So it's nice to see if you want to explore the data visually as a text file. And then we have the JSON output, which is very nice and you're going to see that we've integrated it with Python. Okay. If you're interested in querying a particular structure's properties, well, you can do that with the AUID. Okay, so let's say you know the AUID of your system, and you want to say, okay, what is that compound's distance from the hull? So you run the alloy system, you do minus D2H, so distance to the hull, and then you enter in the AUID, and it'll scan through, and then it'll print out what it is. Okay. You can directly query a structure stability criterion. So it's just minus SC and then the AUID, and that'll print out the stability criterion. And then you can actually query. This is not something that's available through the PDF. This is another feature. If you give the coordinates on the convex hull where you want to see what the value of the energy is, you provide Hall energy and then 0.25. So what does that mean? That means that, so the convex hull, we typically think about the convex hull as being a set of points, but there's a whole facet that's there, right? So the points define a facet. So let's say I want to find the energy of the hull at this point here, in the middle of these 3 points. So you give the coordinates. So this is a 3-dimensional hull, so you only need to give 2 coordinates because the third is 1 minus the plus of the sum of the other. So you give those other coordinates, and it'll actually tell you what is the energy, what is the Z value right at that point, okay? What is the energy value? So you can run that together in the small groups. You can run these commands in the small groups. We actually have some nice high throughput inputs that you can run. So I think we talked a little bit about this with, it's sort of a similar setup. I'm not going to run it now while we're in presentation mode, but you can actually do it together. So I'm going to show you what's going on here. Copy. So okay, paste. So I'm going to close out because I don't want it to run yet. I just want to show you what's going on. So what it's doing now, okay, so basically the algorithm is going to go in and it performs the analysis as you run the command, okay? So it's not like we've pre-computed the convex hull. We do it for the visualization online, but for the actual, when you actually run it from the terminal, it's actually going to go in, query our APIs, and grab back the data and perform the analysis for you because the data changes every day. So in this analysis, I've actually given it 2 inputs, giving back the convex hull, and it's comma separated by MN. I want the MNPT one and the PDPT. So in the input here, sorry, in the output, you can see that it recognized that there's actually 2 convex hulls you want, and it's going to start with the first one. Okay, so that's one way, it's comma separated. If you do a colon instead, you're kind of specifying the sites. Remember from analysis before, it's kind of a similar approach to with the sites. Okay, so paste. So this is actually going to do the exact same thing as the command before, where it's going to run MNPD and also MNPT. Okay, let me zoom in. It's going to run MNPD and then MNPT. Okay, and then we actually have another alias to everything in our database, in the lib2 database. And I'm not going to run the full command. I'll exit again, but I'm just going to show you what it's going to do. Okay, so it recognizes this as an alias, and it knows what all of the elements are in our lib2 database. And so it saw it and it said, okay, I'm going to do, you know, almost 1,500 convex hulls. Okay, so that's why I'm not going to run it. It'll take a while, but that's the sort of power with the command line, is that you can actually run these. You can run these with this analysis here, all in one command. And if you're interested in seeing more of these options, you can just run the same formula, AFLOW minus readme equals the CHULL. Okay. All right. So that's the command line. I'm going to show you. I want to show you basically 3 different variants to interact with the convex hull, and then we're going to go to small groups, and you get to play with which one you want to play with to interact with the convex hull module. So we have our Python interface as well for the convex hull. And so I'll show you where the scripts are in a second, but you know, you basically import the convex hull application. You need to specify what where your binary is. In this case, it's just the one in the path, AFLOW. You give it the alloy system, and then you say, give me the hull, give me all the data in the hull for this alloy system. So this is going to print out that giant JSON for all the data in the convex hull. Then we have the get distance to hull. So that's like the --- D2H command, and you feed in the AUID. And you can see that there's even an options flag. So if there's something on the command line that you want to pass in, like if you want to keep the log file of everything that's going on with the algorithm, it's very verbose. You can keep that file by adding -- keep log. You have your get stability criterion command here as well. You feed in an AUID. And then you have the get energy, which you feed in a vector of the stoichiometric coordinates that you want to specify. So since this is a binary, we only need to give one coordinate, so it's 0.5. Okay, so that means half of this and half of that. If it's a ternary, you only need to give 2, because again, the last one is just the sum of the others. Okay, and there's a README there, and I'll show you in a second where all those things are. You can also interact with it from a Jupyter notebook perspective. Okay, and I'll show you how to launch that in a second. But basically, you're going to run this command: AFLOW Convex Hull Alloy, same thing as before, and you're going to print out either Jupyter, Jupyter 3, or Jupyter 2. So we have a few different variants depending on what system you're running. Obviously, Jupyter 2 is more or less obsolete per standard Python, the standards, if you will. So the default now is Jupyter 3. So if you just put Jupyter, it'll give you the Jupyter 3 default. And I'll show you. You don't need to do it for our setup here because we've already gone through the process of installing the requirements. So you don't need to worry about that. But if you can run this on your computer. You can download AFLOW and run this package on your computer. And if you do, then you want to make sure you have all the requirements that you need for visualizing the convex hull. All right, so to run it, you just run Jupyter notebook and then notebook IPYMB, and that's an output file from this command. And so I'm going to show you here because I've already done it. One second. So I've already opened it up, and I just want to show you what you should expect if you run it. Hold on. Okay, so if you can launch this, you just, you run that command, you go inside of the directory that it creates, and then you run Jupyter notebook. And if you do it with a ternary, with a binary, you just, for those of you that are familiar with Jupyter, you hit enter for this cell to load in the module, enter for this, so you specified a particular alloy system, and then you say plot the alloy system. And you can see that we have a nice visualization here. And what's nice is this is a little finicky, so I have to play with it. But this, you can just click on this, and this is going to open up the entry page. So just like the other one. All right. So that's a nice thing there. And you can do the same for the ternary. So here we have the ternary system. And you click, and you get back your entry page too. Okay. So there's now at least 3 ways you can interact with the convex hull module. We're going to go into small groups in a second to do the exercises, but I just want you to keep in mind. So most of the data can come from the PDF. So I really recommend for the majority of the questions, you're just going to need to go to the actual website and download the PDF. And that's it. You have most of the data there. The data you won't have is if, for instance, you want to query a particular energy point at the hull, right? That's not available in the PDF. So you're going to need to do that from the command line. So you can choose the command line, you can choose the Python interface, or you can choose the Jupyter notebook to run it with. So there's 3 ways to interact with it. So here are the exercises. I don't need to go into presentation mode. All right. So the first question is, what is the distance of this particular compound from the hull? Okay. So that's something you should be able to get from the PDF. It's something you should be able to get from the command line or the Python interface, Jupyter, whatever you need. What is the stability criterion? Okay, so notice I'm implying that this is an unstable point here. I'm implying here that this is a stable point because it has a stability criterion. So what is the stability criterion of this stable point? Here, this is a query. What is the energy of the hull at the concentration 0.5? Okay. And then the last question, which is, I think it's kind of intuitive what I'm asking here, but we want to ask the question, what is the most stable structure on the MMPDPT hull? So I guess it's not really ruining the surprise, but this is based on the stability criterion. So it's a question gauged to what is the one that has, let's say, the largest stability criterion. So that's what the question is querying after. All right, so we'll go ahead and break out to our sessions now. We have 18 minutes to go. So We're going to stay there till about 4:30 Central Time, and then we'll come back and I'll turn it over to Rico. Oh, and I guess we can go through some of the answers too. I think we're starting to get people back. I just wanted to go through the answers very quickly, and there was one or two things that I wanted to show you. So let me share my screen. Okay, the vast majority of these could be done very easily. They could be done very easily with the PDFs. So we're going to open up the AFLOW-CHULL PDF here. Something I didn't emphasize when we were in the main session. This is a working document, so there's a bunch of links embedded in the document. So if I click, for instance, here, it's going to bring me to that part of the PDF. Okay. And there's links embedded everywhere. These are all internal links to different parts of the PDF, okay? And then if you click on this link, this will actually bring you to the entry page, okay? The links that are under these are the prototypes. So those links actually bring you to the entry page. So I can show you very quickly what the answers were. Let's see, where is this one? This one was a few pages down right here. There's a system. So you should have saw that it was 243. Let me zoom in. This system was 243 MeV per atom above the hull. So it's pretty unstable. Stability criterion of TEZR. So that one is on the hull. So this is going to be pretty easy to find. See, it brings us right to it. And the stability criterion is 49 MeV per atom. The energy of the hull, you would have had to have run that through the command line. So let me show you my command line. And so the command I ran was -CHULL -alloy equals CuZR, and then hull energy at 0.5. And you should have gotten about -158 MeV per atom. Okay, and you could verify that on the hull itself. I think I had the picture up somewhere. Oh, I had it up somewhere. Oh, this is a T. Yeah, I had it up somewhere, but you can actually go to the hull and actually see what you were expecting, and it was something under about 200. And the most stable structure, we didn't pick it by accident. Let me pull up the hull. So if you do it based on the stability criterion, it's the first one. So this has the largest stability criterion. This is actually the magnetic system that we discovered. You know, so it is well, I guess another sort of interpretation of the stability criterion is the importance of that point. So remember, what is the stability criterion doing? Well, we're imagining that we take this point off the hull, we recalculate the hull, and then calculate the distance of this point to the new hull. So in effect, it's really measuring the importance of that point to the hull. And so by removing it, we see that the hull really changes. Okay, so there's a big distance of distance of change. That part of the hull is now very new. Okay, so because we don't have that point anymore. So this point is in fact very, very important, and it is a point that it's a material that we first predicted using this analysis, this exact analysis that you're doing today, and then we were able to synthesize it. So that covers that. I think that was everything. And I just want to check that there aren't any lingering questions. I'm going to pull up. I don't have the chat open. 1 second. I just want to check that there aren't any lingering questions before I turn it over to Rico, and then he'll have the rest of the time. Oh, we did get it. Can you explain why the stability criterion is a better measure of most stable structure rather than just the formation enthalpy? It's a great question. So the formation enthalpy, yes, the formation enthalpy, you can consider it as a measure of what is most stable, right? So the formation enthalpy, let me get a binary up. So why would you consider the stability criterion instead of the formation enthalpy? So the formation enthalpy, remember that the formation enthalpy is defined only with respect to the endpoints, okay? So only the endpoints here are zeroed out, right, if you will, so that's how the formation enthalpy is measured. But remember that destabilization of a compound, not everything is going to decompose into its components. It will decompose into, in this case, in this case, it's actually going to decompose into a set of binaries, right? And we have all of the different variations. Systems here, these points are going to decompose into a combination of this compound and the unary, right, and the pure component. So the formation enthalpy captures destabilization with respect to the endpoint, but the stability criterion actually it's a measure of the whole convex hull. So all of the points in that local region, okay? And that's why it's a nice measure of stability, because it really considers your local environment with respect to concentration, right? And so we're working within we're working within the grand canonical ensemble, where not only you're varying you're not only varying temperature, pressure, but you're also varying the concentration, number of atoms. Okay, so that's why it's a better measure of it. I hope that answers the question. Perfect. Any other questions? Okay. Otherwise, I'll turn it over to Rico now. Rico Frederick, who's going to present on an important, very, very important correction for polar materials. So I'm going to stop sharing, and you can